Okay, this starts us off here, section 1 of the book, DC Circuits. You've had the opportunity to do your homework with these chapters. So the ideal thing again is for you to first, what I like to do is read through the chapter as a whole, read the objectives, read through the chapter as a whole, then go through the chapter and then line by line any of the examples and questions that they ask you, try to answer those questions utilizing the book. Then when you get to the back of the chapter, go ahead and do any of those chapter review questions. So if you've read through it once, read through it slowly and did the homework assignment, and then did all the chapter and assignments, then have the opportunity to get together with your mentor. And I know this is the beginning of the quarter, there's a lot of confusion with making it all work out, okay? We'll work those bugs out, trust me, it works. It just takes time. You do your corrections. If you get some wrong, you discuss why you got it wrong, figure it out, and then we do the lecture. Once we go through the lecture, I welcome any questions or concerns or problems that you're having with the material, and then I'll lay those to rest. And then the very last thing that you do is, well, not the last thing you do, the next thing you do is take the quiz. After you take the quiz, if you miss any questions on the quiz, then you can go ahead and do those corrections and get those points back. The very last thing that you do is take the final examination. When you take the final examination, you can't do any corrections. The score you get is the score you get. So I'll give you chances all along the way to make corrections so that you make sure you understand the material and you can retain the material and have, understand it well.
So the quiz you do throughout the course, are they going to, the questions, the quiz going to be the final exam?
A lot of the questions on the final exam come from the same database. I've got a huge database that I've built of all questions. And a lot of those questions, too, you may not like those questions. You may say, this question is a lousy question or whatever. A lot of these questions come directly from industry tests. So don't blame me, okay? All that I'm doing is giving you exposure to those same types of questions that are given on certification tests and company employment tests. Before a company hires you, they're typically going to sit you down and give you a test to see what you know about electricity and electronics. So a lot of those questions are in the database. So I can't guarantee they're the same questions, but probably if you talk with your mentor, they'll say, oh yeah, a lot of the questions on the final exam are the same questions that we saw in the quiz, because they come from the same database. So I'm not going to intentionally make it your final exam more difficult for you. That's not my job. As a matter of fact, if you follow the recipe that I just shared with you, the easiest thing you do this quarter will be taking the final exam. It really is. If you've done your homework, if you've done your lab, if you've attended a lecture, if you've taken the notes, the easiest thing that you do is going to be that final exam. Absolutely. Yep. And everything I say in lecture. Also, from a lot of people I see you've got notebooks out, that's good. A lot of students, they sit there, they don't take notes. And then they wonder where these questions come from. They come out of lecture. Why do you think I'm lecturing? This is what I enjoy doing. Question?
I'm thinking about career. Question about career.
The career? There could be. I'm not going to go out of my way to ask a lot of career questions in the LEC 110. Yeah, the same type of questions that we're asking you as the homework. Yeah. No surprises. I'm not going to surprise you. I've never had any students come to me and say, you surprised me with this question. No, it's all the same questions. We'll schedule that sometime then. So probably before the last week before. Yeah. Okay, so let's get things started here with Section 1, DC Circuits, Chapter 1, the Fundamentals of Electricity. One of the first things that I do when we go through a chapter like this is I'm going to read through these objectives. These objectives are right out of your syllabus. Okay, these should be the same objectives that are in your syllabus. I go through the objectives because this is like preparing your mind for what you're about to receive. This is like formatting your hard drive up here on what it is that you're going to be downloading or uploading, okay? Objectives after completing this chapter, you, the student, are going to be able to define matter, element, and molecule, list the parts of an atom, define the valence shell of an atom, identify the unit for measuring current, draw the symbol used to represent current flow in a circuit, describe the difference between conductors and insulators and semiconductors, define difference of potential, electromotive force, and voltage, draw the symbol used to represent voltage, identify the unit used to measure voltage, define resistance, identify characteristics of resistance in a circuit, identify the unit for measuring resistance, and draw the symbol used to represent resistance in a circuit. The first thing that we're going to talk about is matter. Matter is anything that occupies space. Matter is anything that has weight. Does anybody know what we call the absence of matter? Is there such a place as the absence of matter where there is no matter? Space. That's why it's called space, because it is empty. It is space. There is no matter. Can we create space here on Earth? And if so, why would we want to do so? Very good. In a vacuum. Industrial vacuum. We use industrial vacuum not for cleaning. We use industrial vacuum for removing all of the matter from a space so that only the ingredients, only the materials that we put into the vacuum are there. This is one of the processes that's used in semiconductor manufacturing. Like when they make transistors or microprocessors, they make it in a clean room. A lot of the machines utilize industrial vacuum to remove all the matter from the chamber that doesn't belong. So only the stuff that is there is only what's supposed to be there is what's actually there. Does that make sense? Elements are the basic building blocks of nature. Elements are materials that cannot be reduced to a simpler substance by chemical means. There are over 100 known elements. A lot of you may be familiar with the elements from school on the periodic table. In school, your teacher may have had a pull down. They pulled it down and it had the periodic table on it. Okay? We're concerned not only with the elements, but we're concerned with what makes up the elements. And what makes up the elements in the pure form are atoms. Atoms. And we're not only concerned with the makeup of atoms, but we're concerned with how the atoms are put together. The first part of the atom is the nucleus. The nucleus is located in the center of the atom. This includes protons, neutrons, and electrons. Protons, neutrons, and electrons. Protons are positively charged particles that reside in the nucleus of the atom. Neutrons are uncharged particles that reside in the nucleus. And electrons are negatively charged particles that orbit the nucleus. Now, one of the things that I want to point out to you is this is the first reference to electricity. This is the very first reference to electricity that I've made, right? Positively charged particles for the protons. Electrons, negatively charged particles. Positive and negative is an attribute of electricity. So this shows that atoms have inherent electrical qualities to begin with. That's why we're teaching you about this, because this lesson here, this chapter, is the beginning of electricity. So if you understand this, you understand how the whole foundation of electronics and electricity is built, because this is the energy that we're going to harness. Make sense? This is what it looks like. Kind of, sort of. This is an artist's depiction of an atom. This is the nucleus. The nucleus contains proton and the neutron. Proton is positively charged, the neutron is neutral in charge, has no charge. Outside of the nucleus is this electron that follows this orbital path. It orbits the nucleus. The only thing that's not accurate about this illustration is scale. If the neutron and the proton were this big and this was the nucleus, the electron would be probably about the size of my laser point here. It'd be tiny. The neutron and the proton have a lot of mass. They're huge. They're big. Right? The nucleus contains those. It's very massive. Electrons orbit around the outside and they're tiny. Also the scale. This shows that they're orbiting pretty close to the nucleus. They're actually orbiting pretty far away from the nucleus. So the scale of this picture is wrong, but it's not that important. That, I just want you to be aware of that. A couple of the numbers that you need to be familiar with. One is the atomic number. Atomic number. Atomic number is the number of protons in the nucleus of an atom. Atomic number, the number of protons in the nucleus of an atom. So all the scientist has to do is count the number of protons, and if you count 13, it's got an atomic number of 13. If you count 14, it's got an atomic number of 14. Because no two elements, different elements, can have the same number of protons. They have to be different. That's how materials, elements, get their number on the periodic table. There's no repetition. Another number that's used on the periodic table is atomic weight. Atomic weight dictates the mass of an atom. We determine the atomic weight by simply counting up the total number of protons and neutrons in the nucleus. Counting the number of protons and neutrons in the nucleus. Any questions on that? It could be the difference of a couple numbers. Okay? Typically, like, let's say there's 7 protons, there may be 7 neutrons or 8 neutrons. So the atomic weight is not always double the number. It could be double or a few more than double. But this actually shows the mass of an atom, the weight, as where the atomic number is just simply counting up the number of protons. Very simple. Another term you need to familiarize yourself with is the term shell. Shell. Shell is where the electrons orbit. Shell forms concentric circles around the nucleus. The shell is filled in sequence. The shell is filled in sequence. Meaning, this is almost like, have any of you been to the airport, SeaTac Airport, the parking garage? What happens when the first level of the parking garage gets full? What do? You go to the next level. When that level is full, what do? You go to the next level. Actually, you know what I started doing last week in Las Vegas? Every night I would go over to Caesar's Palace to have a cigar. you know what I started doing? Just driving directly to the top level. So I didn't have to look for a parking space. But that kind of ruins my story. For the most part, the shells fill the first level, then it fills the second level, and there's a map that's associated with that. When they get full, I'm not going to have you remember that. But I just want you to know that when a shell gets full, it goes to the next level. When that gets full, the next level, and it works like that. We're going to get to that in a minute. There's a number of different shells. We'll talk about that in a minute. The next shell I want to talk about, though, is the valence shell. And the valence shell is the outermost shell. Whatever the outermost shell is. If we fill 3 shells, the outermost shell will be that third shell. That's the valence shell. And to be honest with you, this is the shell that we're interested in electronics, in electricity, because that's where things are going to happen with electronics and electricity. Valence refers to the number of electrons contained in the valence shell. This is the answer to your question. How many shells are there? These are the shells that we know about, that science has discovered, if you will. And the innermost shell, the first shell to get filled, is the K shell. From the K shell, it goes up to the L, M, N, O, P, Q. So we haven't discovered anything that has any electrons further out than the Q shell. Even when we went to the moon and we got moon rocks and brought them back and analyzed them, we didn't find some new element that had something in a shell beyond the Q shell. Why did they start with the letter K? Why didn't they start with the letter A? I don't know. Maybe because they assume there might be something there that they don't know about. That's why you're in college. Okay? Because if you ask anybody on the street, what's the first shell going to be called? They probably say it's called the first shell or the A shell. It's like, no, I've got a college education. It's the K shell is the first shell.
So when it goes from K and then it goes to L and M and
yep.
What happens if it goes to Q?
If it goes to Q, that means it's a very high number on the periodic table, right? Because an element has an equal number of protons and electrons. So if I've got electrons in the Q shell, that tells me that this is a very complex atom, that it's a very high number on a periodic table. Okay? Why am I talking to you about this? That's a good question. I wish I had me as an electronics teacher when I was in school, because when my teacher would talk about a lot of this stuff, I'm like, why are you teaching me? I'm not an atomic scientist. I want to be an electronics technician. Why are you teaching me about all of this? Because you need to understand this, because this is the foundation that all electricity and electronics are built on. The first material that I want to introduce you to is the material called a conductor. Are any of you familiar with conductors? Have you heard that term before? What's a common electrical conductor? What do we use? Wire. Wire. Okay? Conductor, by definition, is a material that contains a large number of free electrons. That's what's in the book. So that is what you may see on the quiz as well. But there's also an easier way that I want you to remember it. A conductor is any element that has 3 or fewer electrons in the valence shell. A conductor is any element that has 3 or fewer electrons in the valence shell. Does that make sense to you? So if it's got 3 or fewer electrons in the valence shell, what does that tell you about the valence shell? What does that tell you about that level of the parking garage? It has what? It has space. It has space. 3 is a low number. I'm sorry, because I didn't tell you how many it takes. The 3 is kind of a small number, so that means, if there's only 3 cars parked up there, there's space for me. That's what makes it a good conductor. If we look at the table here, figure 1.5, This shows silver, copper, gold, aluminum, tungsten, iron, nichrome. Silver is the material that has the best conductance. That means silver is the best conductor. How many of you are familiar with silver wire? Silver solder, we've heard of. What about wire? The best conductor, I'm not lying, the best conductor that we have found in nature is silver. When I was at the Consumer Electronics Show last week in Las Vegas, I saw a lot of gold connectors. Why are they selling gold connectors when silver is the best?
They don't need that much silver.
No. Why down there? You guys have been to the stores before, right? You've seen the gold-plated conductors for the back of your stereo and your television. Why gold when silver is the best?
Well, chemicals are something where environment where you work for something is not rusting.
Not rusting?
No. Something is looking at chemicals or together with the environment, but chemicals
No, that's a good attempt. And the answer is really simple. I heard you say rust. Not rust, but oxidation. Oxidation. Do any of you have silver jewelry or anything that's silver? What happens to it when you're done polishing it? It looks really nice, right? For how long? Not so long. And then it begins to do what? Tarnish, fade away, oxidize. This is the reason that we don't use silver in electronics, because we live here on planet Earth, which is an oxygen-rich environment. It would begin to oxidize. Then it makes an electrical connection that's not so good. Copper. Does copper oxidize? Yeah, copper oxidizes and tarnishes as well. So it's the same problem. Do we use a lot of copper wire? Yeah. And why do we use it? Because it's abundant, it's relatively cheap, it's really the best solution for us to move electrical energy from point A to point B. So it makes the most sense. And you could clean the copper to make the connection and make it work. Why do we see so much gold in the industry? It's expensive and it looks nice, but what's the real reason that we use gold plating on a lot of electrical conductors? What's that? Exactly. If you were scuba diving in the Caribbean and you found a treasure chest that some pirate left behind and you opened it up and it was full of gold, you know what it would look like? A treasure chest full of gold, even though it's been under the water for hundreds of years. If you opened a treasure chest and it was full of silver, it wouldn't look so good. It'd be like, what's this? This doesn't look good, you know? But gold doesn't tarnish. So that's the reason that we use gold plating. One of the most popular conductors that we use is gold-plated copper wiring. So if you put that gold plating on it, it won't oxidize. And then if you're putting a male-female connector together that are both gold-plated, they're clean. They're not oxidized. You put them together, you get an excellent electrical connection. Aluminum used to be popular for wiring because it was relatively inexpensive, so they did a lot of wiring. Actually, a lot of older homes have aluminum wiring in it. My home has some aluminum wiring in it. Tungsten, iron, nichrome, this just shows the level of conductivity. But the most important thing I want you to remember is that a conductor is a material that has 3 or fewer electrons in the valence shell. The next material I want to talk to you about is an insulator. Now, by the book's definition, an insulator is a material that prevents the flow of electricity. It's stabilized by absorbing valence electrons. Some of the materials that are good insulators: mica, glass, Teflon, paper, rubber, bakelite, oil, porcelain, air, are all good insulators. Mica is actually the best. I have here an example of mica. Mica is found in rock formations, typically quartz formations. Not so much here in the western United States. I got these somebody was telling me there's a mica mine in eastern Washington. I got these examples from back east. This here, please be careful, it's very fragile. This is mica in its original raw form. Pass that around. And then this is a piece that's a manufactured process. This can be used as an electrical, like a washer, an insulator. Sometimes we want to keep one piece of equipment from another piece of equipment. The important thing I want you to remember about insulators are materials that have 5 or more electrons in the valence shell. If it has 5 or more electrons in the valence shell, what does that tell you? Thank you. Thank you. If it has 5 or more electrons in the valence shell, what does that tell you? Yeah, the parking lot is getting pretty full. So if the parking lot is getting pretty full, your chances of being able to park there are not so good. That's why it's called an insulator. An insulator pushes away these electrons that want to park there.
I always thought that rubber was one of the best.
No, this table is accurate. So mica is really good, glass is your cheap Teflon paper, rubber is good, it's still good, even bakelite. You know what bakelite is? It's like that insulating material. If you have any home appliances, like on your toaster, that it breaks and then you can't glue it together, that's bakelite. It's not only a good electrical insulator, it's also a good thermal insulator. That's a plastic, yep. Oil, a lot of people don't think of oil as being an insulator, but actually a lot of high-power transformers are filled with oils. They used to be filled with a lot of poisonous oils. Now the industry has gotten away from that. Porcelain, and believe it or not, air. Air is a great insulator. If you look at the high voltage wires going through downtown Totem Lake out here, what are they separated by? They use big glass insulators, but they're actually separated by what? Air. They're just hanging there in the air, suspended. That's a tough question. I would probably have to say some type of a plastic, because for the most part when we go and buy wire, if we're going to wire our car or wire our home, it's going to be some type of poly, some type of plastic material. A lot of companies continue to do research to come up with new types of insulators, and that's a very good question. A lot of people don't look at that. They think wire is just wire. Wire is not wire. Several years ago, Boeing was using wire produced by, I think it was DuPont, and the insulator was called Kapton, and it was some type of synthetic whatever. The problem was that it didn't last. So the solution was, years after you bought a Boeing airplane and the electrical connectors, the insulators failed, basically the remedy was to disassemble the airplane, remove the wiring, rewire the aircraft, and reassemble the airplane. You know what they did with those airplanes? Flew them to the desert and parked them. It wasn't cost effective to repair it. This was actually one of the big concerns that I had even with my automobile, is shortly after I got my last car, I had some wiring harness problems. And I actually noticed where my wire, the insulation was degrading. I think what happened was that some animal was climbing up in my engine compartment and chewing on the wire. And that was, so I re-insulated it, and there's nothing you can do. I mean, if some type of a rodent wants to get up there and chew on your wiring, I don't know what you could do to keep it away, because that's a real problem. But different companies are constantly looking for different types of insulators. And even, this is something, again, that is so profound that impacts all of us. Even if you've ever gotten a set of jumper wires to jump-start a car, what makes the difference in a good set of jumper wires as opposed to a bad set of jumper wires? The type of insulation that's used, and also the thickness of the conductor that's used. So if you go to Fred Meyer and you buy a set of jumper cables for $4.99, if you went to Napa down the hill and paid $90, you're probably getting a really, really thick conductor, and you're also probably getting a very flexible rubber that's thick and it makes it easy and nice for you to coil up instead of a hard plastic that. So there really is a difference in conductors. And much safer. Yeah. So it really makes a difference. So that's one of the things. This is such an important lecture that even when I was showing you this morning from the Consumer Electronics Show, a lot of these companies, like you've heard of Monster Wire, Monster Wire is just, called Monster Wire, so people think, oh, I got to have Monster Wire. All of it is a company that manufactures. They don't even manufacture it. They have a wire company manufacture it to their specifications. A really big conductor with really good flexible insulation around it. And it's very expensive if you want to buy that for your home audio system. But all of it is wire. You know what I typically use around my house for wiring up speakers and stuff like that? The cheapest wire I can find. I usually call friends of mine that work in industry and they say, hey, do you have any wire laying around? What are you looking for? The thickest wire that you could give me. That's the best wire for me, and that's because it's the cheapest. But that's what, my criteria is. So the same thing even if you're doing electrical wiring, electrical code specifies minimum gauges of wire to deliver the energy. But a lot of times electricians, they don't even look at the insulation. They just, whatever the supplier gives them is good enough. So that's what drives insulators. So a good conductor is 3 or fewer electrons in the valence shell. A good insulator is 5 or more. What number is between 3 and 5? 4. Very good. You're good at math. Our resident math whiz. If you've got a material that has 4 electrons in the valence shell, that means it potentially could be a good semiconductor. A semiconductor can be altered to function as either a conductor or an insulator. This is what makes diodes, transistors, all of these sorts of components. They're components that could be influenced to either be a better conductor or a better insulator. You're going to learn more about those next quarter in ELEC 120. Negative ion. Here's an important term you need to understand. A negative ion is a negatively charged atom. A positive ion is a positively charged atom. The first thing I want to share with you is that in the beginning, whenever the beginning was, and whoever was responsible for the beginning, everything, meaning all matter, was in a neutral, natural state. A neutral, natural state. Matter will just sit in a neutral, natural state until we do something to it. Okay? I'm going to walk over here to this table, and I'm going to go ahead and get a chair. This chair is made up of what? I'm going to put in the answer. What's this chair made up of? Plastic and metal. Even an easier answer than that. Matter. Very good. The answer is always matter. What's this made up of? Matter. You can't go wrong if you give me that answer. Okay? So this is matter. And I assume that this right here is sitting here in a neutral, natural state. You all agree? Now, when I go ahead here, get my handkerchief out, and I start rubbing on this chair, what am I doing? What am I doing? What's taking place? Anything? Am I just cleaning the chair? Friction. There's probably friction because I'm rubbing it with my handkerchief back and forth very rapidly, and I can actually feel it. It's getting a little bit warm. Right? By me applying friction to this chair, I am applying energy to this chair. You all agree with me? Now, since I'm applying energy to this chair, there's probably a really good chance that I am doing what? At an atomic level. What I want you to do for a moment is think about think about those cars parked on the upper level of the parking lot, and all of a sudden some giant comes by and is rubbing with a handkerchief. What's there a chance that might happen? Yeah, I might be disrupting or moving some electrons in the valence shell. Do you all agree with that? You know what I just did by rubbing this chair? I just made electricity. I don't see any lights coming on, or I don't see any static or anything, but I did make a small amount of electricity. This is static electricity that I just created. Very small amount, but I just created it. How? Because I know that when I impart energy on matter, I can free an electron and cause ionization. When ionization has occurred, I've created electric energy. That's why, again, this lecture is so important. It's so important because this shows the beginning of where electricity came from. Any questions on that? So if I apply energy to matter, I can create electricity. In this particular case, it was static electricity. So ionization is the process of gaining or losing electrons, and it's very significant in current flow. You're going to hear about this term throughout your career in electronics. If you go for your degree and you learn about communications electronics, you're going to learn a lot more about ionization. As a matter of fact, there is a layer of the atmosphere that is called the ionosphere. The ionosphere, and it's a layer of the atmosphere. And you know what the ionosphere plays a very important part in? It's preventing some stuff coming through from space, but as it pertains to electronics, it's very critical in communications. AM radio signals, like listening to Cairo, Como, KVI, AM radio signals, bounce off the ionosphere. Bounce off the ionosphere. At night. At night. During the day, they just keep going. So like tonight, after dark, if you were playing with your AM radio dial, you stand a really good chance of listening to a San Francisco radio station here in Seattle. Why? Because that signal will come up with the ionosphere and then bounce off. Why do they call it the ionosphere? Because it's a layer of the atmosphere that ionizes when the sunlight hits it. And when does the sunlight hit it? Sunrise. So when sun rises, it hits the ionosphere, ionizes the gas, and that allows signals to just go right through it. After sunset, the gas is cool, it goes back to its neutral natural state, radio signals bounce off of it. This is one of the reasons that radio stations have to turn their power down at night. If they didn't, AM radio stations, if they didn't turn their power down at night, you would hear a San Francisco radio station as clear as you would hear a Seattle station. And that's not good. The Seattle station, if there was an emergency or something, why am I listening to a San Francisco traffic report? Doesn't do you any good. So the Federal Communications Commission makes these transmitters turn their power down at night because of the ionosphere. So you're going to hear a lot about ionization later on in your career in electronics. This is the last time you're going to hear it. Now, current. Has any of you heard the term current before? Yeah, current. Electrical current. It's a very common term that we use in electricity. We're going to define that term right here. Current is the movement of electrons from negatively charged atoms to positively charged atoms. Current is the movement of electrons from negative to positive. It's represented as a capital letter I. So if I give you a question that says I equals question mark, I'm saying what is the current equal? Another term you need to familiarize yourself with is the term Coulomb. Coulomb is named after an individual by the name of Charles Coulomb, Frenchman, who dedicated his life to counting electrons. When he got to this number, 6.24 times 10 to the 18th, he died. So they called that a Coulomb. So like, does anybody want to continue Chuck's work? Anybody? Any? No? We'll call it even. 6.24 times 10 to the 18th. So this is like a gallon of gas, it's like a dozen eggs, it's like a barrel of oil. It's a quantity of measurement. It's a very big number. I'll show you how big it is actually next chapter. And we represent that as a capital letter C. Mm-hmm. Nah, I would memorize them. No. The term we use to really measure current is the ampere. Ampere is named after Andre Marie Ampere, and what ampere came up with is a correlation between a coulomb and time. 1 ampere is 1 coulomb moving past a single point in 1 second. Current is measured in amperes. Circuit breakers, fuses, they're all measured in amperes. It's represented with the capital letter A. So I would equal 10A. Current equals 10 amps. Named after Andre Ampere. Potential is the ability of the source to perform electrical work. The more energy I apply to matter, the greater the difference in potential I could create. Difference in potential causes electrons to move or flow in a circuit, and it's referenced as electromotive force, EMF, or what we know as voltage. Voltage is that force that moves the electrons in the circuit. We cannot have current without voltage. We must have voltage in order for us to have current. Voltage is the pressure or pump, if you will, that moves the electrons. It's abbreviated with either the capital letter E here in this book, or you could use the capital letter V. Different books use different letters. It's unimportant. You could use whatever you want to use. E or V, I know what you're talking about. The unit of measure is called the volt. Voltage is that force that moves the electrons in the circuit. We cannot have current without voltage. We must have voltage in order for us to have current. Voltage is the pressure or pump, if you will, that moves the electrons. It's abbreviated with either the capital letter E here in this book, or you can use the capital letter V. Different books use different letters. It's unimportant. You can use whatever you want to use. E or V, I know. Another critical electrical property is the property of resistance. This is the opposition to the flow of electrons. Resistance is the degree of resistance depends on size, shape, or temperature. Measured in ohms, named after George Simon Ohm, and it's represented by the Greek letter omega. The Greek letter omega. Conductors have low resistance to current flow because they have many free electrons, and they have 3 or fewer electrons in the valence shell. Insulators have high resistance to current flow, few free electrons, meaning they have 5 or greater electrons in the valence shell. In summary, we talked about matter. Matter is everything that makes up everything. The absence of matter is defined as space. We could create space here on Earth with a vacuum, an industrial vacuum, where we pull all the matter out of a chamber. Elements are the basic building block of matter, and we have about 100 or so that we know of. And we know of everything. And even when we went to the moon, we didn't discover any new ones. So scientists have got a pretty good handle on everything that's made up, which is actually pretty wild if you think about it. I don't want to get this into a religious lecture or anything like that, but, God made all of this, whoever your God is, really only needed 100 plus different ingredients. Me, you, that chair, that table, the wall, my car, a gallon of gasoline, a carton of eggs, it's all made up of the same 100 plus ingredients. When we chemically combine those different ingredients, we end up with what are called compounds. Compounds. The smallest particle of a compound that we could have is called a molecule. The smallest particle of an element that we could have is called an atom. And that's what we talked about. Specifically, the makeup of atoms. Nucleus, protons, neutrons, and electrons. The most important particles, if you ask me, they're all pretty important. Without them, we wouldn't have any of them. Protons, positive charge, electrons, negative charge. And everything found in nature is in a neutral natural state until we apply energy to it. Atomic number is derived by counting the number of protons. Atomic weight is derived by counting the number of protons and neutrons, which shows you how dense they are. We don't even count the electrons. All we do is count the protons, neutrons. We call that the atomic weight. Shell is the orbital path that the electrons follow around the nucleus. Question?
I don't know how to make the molecule. Between the atom, more parts of the compound, because the compound is produced from the molecule, but atom is most the molecule. Can I say that it's smallest part of the air?
The smallest part of an atom?
No.
The smallest part
of the compound of the element of the molecule of the air. Because the atom is smallest part of the element, but molecule is smallest part of the compound.
For it to retain its identity, just be very careful how you answer that question on a quiz. If I say, what is the smallest particle of a compound? Molecule.
But the smallest part of the molecule is the same, not the atom.
Yeah. Just be careful how it's worded. And if I say, what is the smallest particle of an element? Atom. Very good. Have you been looking at the quiz? Those are exactly the types of questions I ask on the quiz. And I try not to be tricky because it's tricky, but you just have to read the question and make sure you know what I'm looking for. Okay, ionization is the process of either giving up an electron or gathering a free electron. And it's important that you understand that. Ionization has nothing to do with the proton or the neutron. Okay? We won't do anything inside the nucleus of the atom. Okay? We don't do that. That's like splitting the atom and it causes atomic bombs to go off. So all we're doing is playing with the valence shell. Current is the flow of electrons in a circuit. Coulomb is a number of electrons. 6.24 times 10 to the 18th makes up 1 coulomb. Ampere is coulombs per second. Ampere is the unit that we use to measure current in. Electric current is that flow of energy. Think of it as a river. When I say current, think of it as a river. And potential and electromotive force, this here describes voltage, the force that makes the current flow inside a circuit. Does anyone have any questions on anything we covered here in Chapter 1? Yes? No. Current is the flow. This is the pressure. This is voltage. This is current.
No, just voltage is electromotive force. Sorry, one wrong question. If they put 2 times ampere and electric current is maybe I think it's wrong question. But voltage and electromotive force.
Voltage and electromotive force are the same thing, yes. Yep. Yep. Okay. Any other questions on Chapter 1? Section question? Sure, what's the question?
What action causes current in the electric circuit? That's going to compute voltage?
Can you have current without voltage? No, you must have voltage, that difference in potential, before you could have current. Okay? Another question, sure.
There is two theories, I know, about voltage.
Mm-hmm.
From plus minus, from positive negative,
Yep.
from negative to positive.
Sure. You're talking about electron flow versus hole flow. We assume that electrons flow from negative to positive. Why? Because when we apply energy to matter, we free the electron and then it flows negative to positive. Some schools, some universities, scientists, study what's called hole flow. They assume that the hole, the absence of the electron, is flowing from positive to negative. So some books that you open up, if you go to the library and open up an electronics book, it may show current flowing positive to negative. That assumes hole flow. We don't study that here. Most community colleges, technical colleges, high school, the military, a lot of universities all study electron flow. A lot of researchers study hole flow. We are going to talk more about hole flow when you get into ELEC 120 and we talk about semiconductors, because understanding hole flow is critical in understanding how that works. Okay? Any other questions? Okay, if not, that does it for Chapter 1.